Good morning. The joke for today. Why do bees have sticky hair? They use honeycombs.
Because you use combs in your hair. And honeycombs, bees make them. Anywho, all right, everyone. Hello. Welcome. I was like, what's up with this? We went farther than this. So today, we are going to, yeah. There's note cards up here. I promised you note cards, and there are note cards. So there's 5x8 note cards. Behold. 5x8 note cards. So they're a bit bigger than a normal note card. They're not the 3x5. You can write on the front and the back. I don't care what you put on it. I don't care how tiny you write. I don't care how many colors. All I care is that you don't make it into a flip notebook. That's the only, because then it's not a 5x8 note card. It's a bunch of sheets of paper cut to the size of a 5, whatever. You can print things and glue them to it. Just whatever's on there has to be flush. And then the other thing I think I mentioned to you all is you can't share it with someone else. And when I say that, you and someone else can have the exact same note card. Just on the test, you can't pass a note card back and forth between people. Which probably sounds obvious. But I've had people do that in the past. So that's, any policy that someone mentions is generally because someone's done that. And they weren't trying to cheat. Probably just someone forgot their note card. But I don't want to be like monitoring that. That's a pain. So, today or tomorrow, I'm going to send out an announcement with the test details. I've kind of given you all those details already. So it's going to be 20 multiple choice questions, 3 free response, pick 2. 60% of the grade will be the multiple choice. 40% of the grade will be the free response. The free response questions have 2 parts. If you all go to the formula sheet, it is actually... So when you go to the Files tab of Web Courses, you can find this formula sheet. This is the exact formula sheet I'm going to give you. So if there's anything not on here that you want, that's what you want to put on your note card. But this is the exact formula sheet I'm going to give you. Like, it's already on the paper. But on this as well is the rubric for the free response questions. So the free response questions, remember you're going to pick 2 of them. They have 2 parts. So each part is going to be graded with this rubric. And this should not, hopefully this won't be surprising. It matches the 4-step problem solving process. The first points are given, did you draw an accurate picture of it? The second part of points is, did you write down the givens? Did you write down what you're solving for? The next part is, did you find equations that actually let you find what you need, given what you have? The next part is, you set everything up right, but you just flubbed something in your calculator, and then you get all the points if your final answer is correct. Look at that. It matches everything I've been telling you to do this entire time. If you decide not to write anything but the final answer, you're rolling the dice. It's all or nothing. It's just not a good strategy for many reasons. You're more likely to make a mistake. And, I can't read your mind. I can't determine if you got the wrong answer. They're not going to try to guess how you got the wrong answer unless you've written down your process and things like that.
What if you get the right answer but you did some steps pretty wrong?
Pretty much impossible. Yeah. So the question was, it's a good question. What if you get the right answer but you did some steps wrong? That's hard to do. It is actually very tricky to get the right answer by making the wrong steps. The only way that happens if you make 2 mistakes that cancel out each other. But hopefully when you've done the problem sets, you've kind of realized that. The beautiful thing with physics is there is one right answer, and there is enough steps to get to that right answer that if you're not following the right process, you're not going to get there. It's like driving to someone's house. If you don't take the right directions, you're not going to end up at the right spot. It's really hard to end up at someone's house if you go the wrong directions. You can accidentally make a left and then eventually accidentally make a right, and 2 mistakes can cancel each other out. But it's unlikely. It's unlikely. If you don't know how to get there, you're not getting there. So, beautiful thing about physics. Love it. I do not envy classes like English or things like that are more subjective and they actually have to grade papers in detail way more. And don't envy those classes. Never have. Anyway, so there's that. trying to think if there's anything else I need to tell you all. I think that covers it. Any questions about the test or anything? Yeah.
Do we have the option of doing all three written response?
Yeah, that's a great question. Yeah, thanks for asking that. You can do all 3 free response. You will have to select 2 for grading. The third one, we will only look at, and if it's perfect, then we'll give you the points for it. If it is not perfect, we're not going to spend the time on it. So if you do a third one, that's you don't lose anything. If it's absolutely perfect and one of your other ones isn't, yeah, we can quickly look at it and say it's perfect. Grading something that's perfect and grading something that's absolute crap are really quick. It's the in-between that takes a bunch of time. So, yeah, if it's absolutely perfect, we'll look it over and say, yep, all right, great, perfect. Give you the points for that. Replace that with the other one. So it doesn't hurt to do that third one.
By absolutely perfect, you mean like set up well? Like we have this.
Means your final answer is correct in both sections. Means your final answer is correct in both sections. Oh, and there will be multiple versions of the test. So do note that. So obviously, don't cheat. But to dissuade people from being tempted to do so, do note that if you look around, they're not going to have the same numbers as you. They're not going to have the same problems as you, potentially. So, not a good idea. Not a good idea. Also, obviously, if cheating, you cheat, I take away, all the normal cheating policies that are never fun to say, but you know how it goes. There's a statement, cheaters never prosper. Cheaters do prosper until they're caught, and then the consequences are severe. Don't risk it. Don't make me do severe. It's not fun for anyone. It's not fun for you. It's not fun for me. It's not worth it. It is not worth it. Just be prepared. I know it sounds like easier than... All right. So, we only have one last thing I need to teach you all today. Oh, I'll point this out. In our problem set, I actually need to update this end. These are the last 2 problems of the problem set. The last 2 problems. The last 2 problems of the problem set you do not need to do. All right? Number 12 is a banked curve. Feel free to check it out. I actually need to update the answers. It's not quite right. We're not going to do banked curves. We don't have the time for it. And then 13, 13 I will kind of leave here for future generations and for you all. I've told you all that we're not going to calculate air resistance in this class. And number 13 exists to show you how complicated calculating air resistance is. How many things you have to know about the situation and all that jazz. So feel free to look it over if you're like, I want to do a practice problem with air resistance for funsies. I will quickly show you all the equation for it today and then move past. But I'm not going to ask you questions on the test about air resistance. So there you go. Okay, so that leaves us today with only one final thing. So last class we did a lot of things. We did this. We did the light on the strings, and we did a static problem. We then did this pulley problem, and I challenged you all to realize that this problem was actually a one-dimensional problem. It was the 2 objects stuck together. A pulley lets you redirect things and makes an X into a Y, basically. And so you can actually envision the problem like this. I challenge you all to think about that. These pulley problems are really good. They really kind of test whether or not you understand this idea of a free body diagram. So there's that. We then did some things with it. There's some exercise for no reason. Spring force. Spring force, I'm going to straight up tell you, if you haven't noticed, there's no problems about spring force in the problem set. So I mention it because it's good to know. It's fine that we're not going to have any problems on it. So there won't be any problems using the spring force. But when we get to energy, we will reference this and we will use stuff with springs. Whatever, there are forces that exist. Woohoo. Friction force, this one is very important. We talked about static friction and kinetic friction, and we said, why does friction exist? And it's a function of the normal force. I also tried to reinforce to you all that the normal force is not always in the opposite the direction of gravity. It is not always opposite direction of gravity. It's opposite the surface. Anyway, so we talked about that. We talked about a wheel, and that a wheel actually uses static friction, just like your shoes. When you walk forward, it's static friction that pushes you forward. And then we, showed you some numbers for them. We did a problem, woo. And then we did the inclined plane. And I challenged you all here that an inclined plane is just a flat surface that's rotated, where gravity, instead of pointing down, gets a little tilted. So remember, this was an inclined plane. Doesn't look like one because I did the tilting for you. So this was the original problem. It's an inclined plane, and I challenged you all that this is basically just a flat problem, and we have to find the components of gravity, the x and y components. The x component pulls it down the hill. The y component pushes it into the hill. The y component of gravity equals the normal force. This is what our lab's going to be on today. So our lab today is going to be blocks on an inclined plane, finding coefficients of friction. It's going to be a good time. Anyway, so then we talked through this. We talked about how to find the angles. We said that this angle down here is this angle right here. They're the same angle. And then we kind of talked through a few ways that you could figure that out. Then I gave that there. Then we set up a problem, and that's where we left things. We set up that problem. I had you all kind of work through it, see if you can get the answer. And that was it. So there we go. That's a summary of last class, because the reason I wanted to do that is we really don't have that much left. We actually only have 7 slides left or something. So here's that banked curve that I told you you're not going to have to do in this class. It is in here if you want to look at it, but we're not going to spend the time on it. I'm not going to test you on it. I will talk about it for 5 seconds. I will reference the slides, but I'm not going to test you on it. All right. Centripetal force. So the way I've set up this list, I'm looking at it now, I'm not actually happy how I said it. Centripetal force is not necessarily a type of force. Centripetal force is not necessarily a type of force. So what I'm actually going to do is I'm going to copy this, and I'm going to paste it over here, delete all of this, delete this here, and you're like, what is he doing? The most important thing I need to teach you all right now when it comes to centripetal force is not a type of force. It's not like normal. It's not normal force or tension or a spring force. Centripetal is not a fundamental force, I guess in some way. It is a combination of these together. Okay? That is something. So I'm gonna try to express that a few ways today. Let's see. Do I already have some nice things for it, or do I really jump into it? Okay. Let's just go ahead and draw a picture of this. I have some things in the next slide, but let's just kind of hash this out. All right. So I'm going to ask you all a question, actually. Clicker question. A car goes in a clockwise circle as shown, as seen from above. What is the direction of centripetal acceleration when it is on the right side of the circle? Is it up, down, left, right? And I'm going to be so kind and even draw a picture of this for you all. Here's my circle. Clockwise. I am asking the direction of centripetal acceleration when the car is at that dot shown there. I plug in a bunch of things. I open the clicker stuff. Everything works the way I want it to. I have not started it. No, I have not started it. Yeah, I'm opening the software, but you get so much time to think about it. Yeah, this one you want this. The sum of forces to the center equals notoriously a tricky. People like yeah. So that's just going to be a very common conversation. So 30, 40 minutes as you all interact with people. I haven't figured out a great way to. It's for me at least. It's always very hard to convey that idea to people. Yeah. Yeah. So we'll do a couple. Yeah, that'll be good. That's a great idea. I'll see which ones I have. If not, I'll make some new ones. All right, you've had a lot of time to think, so we'll just go to like 45 seconds on this. Should be quick. Which way is centripetal? Key phrase, centripetal. No, I didn't give the answer. I just said the word really slowly. From your perspective looking at this picture. As seen from above. All right. 3, 2, 1. Okay. The answer is towards the center. Centripetal is towards the center. There we go. So the answer is, there it is, to the left. Okay. We are going to sit in this question a little bit longer. We're going to sit in this question a little bit longer. A car is going in a clockwise circle as seen from above. What is the direction of the centripetal force when it's on the right side? Haven't taught you what centripetal force is. See if you can guess. And we'll just leave this open, and while we leave this open, guess what time it is? Time to scan a QR code. Now. You're not putting up one? Oh, is it too big for you? Can't hang. Are you a tea or so? It clearly seems coffee. I'll jump back to it. The question was, what's the direction of centripetal force? I'll jump back to it. I'm not gonna immediately open and say, all right, we're done. That'd be mean. That'd be really mean. Yeah. We'll do this before I forget, because I will forget. I've done it before. I'll do it again. It does the job.
Oh, gosh. Clear.
Yeah. Do you need me to? There we go.
Thanks.
Yeah.
Thank you.
You on your. As always, Leo's got your back. If it's not working for you, call him over. Give me John Hancock. All right. It seems like everyone at least has done this. I don't know. I don't see any phones in the air. All right. Back to the question. What is the direction of centripetal? Oh, sorry. Did I go too quickly? I'm sorry. I was looking for phones in the air and didn't see anyone. No, it's slightly different. Instead of centripetal acceleration, it's what's the direction of centripetal force. Yeah. Haven't taught you this, but go with your gut. All right. We're going to close this out in 3, 2, 1. I have not taught you all, I haven't taught you all the equation for centripetal force yet, But we know Newton's second law. Actually, we don't even need to know Newton's second law. Look at the front. Centripetal force. Center force. Centripetal force also points towards the center. And there's two ways you can figure this out. One, centripetal, center. The other way, F equals ma. So if A points towards the center, F points towards the center. And we're having so much fun with this problem, we're going to do a third version of it. Now, this one is slightly different. A car goes in a clockwise circle as seen from above. What force keeps the car in the circle? What force actually keeps the car in the circle? Notice, none of the options I'm going to list will be centripetal. I'm asking what is the actual force that's keeping the car in the circle. What I'm going to stress to y'all today, centripetal force is not the fundamental force actually causing it. It is the sum of all the forces causing it. So that's the thing I want to stress to y'all today. So our options are normal force, gravitational force, friction force, or tension. I am picking from the options that we've talked about. I guess you know what? Let's go crazy. Spring force. Let's list all the different forces we've talked about. I could technically put, I guess, applied force as well. What is the actual force? What is the actual? I'm going to use the word fundamental. It's not technical. This is flat ground. Flat ground. Very, very important that this is flat ground.
Oh, flat ground.
Very important. This is flat ground that this car is making a turn on. What is actually keeping it in the circle? What is actually keeping it in the circle? It is going in a circle, but why? Something has to push it towards the center. What is it? Is it gravity pushing it towards the center or pulling it? Is it the normal force pushing it towards the center? Is it friction force? What do y'all think? Friction. It would keep going. Yeah, without friction, I go in a circle.
So that concept might go away like the sphere.
So the key here is we know that the force that's keeping the circle has to point towards the center. That's what makes it go in the circle. So then we just have to decide which of those would point towards the circle. The normal force point towards the circle, or the friction force point towards the circle. And we're looking at the same above. So that's the question. So yeah, the key to this is what force is keeping it in the circle? Which force is pointed towards the center? Is it gravity? Is it normal? Is it spring? Is it tension? Is it friction? Which one is pointed towards the center? All right, we're going to close this out in 5, 4, 3, 2, 1. Okay, so the key here is, again, which one points in the direction? So normal force. Which way does normal force point? Away from the surface. So it's very hard for me to draw this. That's out of the screen. The normal force points out of the screen. I can't really draw that accurately on here because it's very hard to draw, like out of the screen. I'll draw it very light. There you go. It looks like it's out. It doesn't look like it's out. Out of the screen is the normal force. That ain't it. That's not what keeping it in a circle. That is what is keeping it from falling through the surface. Gravitational force. Which way does that point? Into the screen. That's not keeping it in a circle. That's just keeping it on the ground. friction force. Which way does that point? And that's the one that's kind of tricky. And the way I think about this, when you turn, when I take a turn, I think of like an extreme case. Say you want to really turn really quickly to the left. You're going to like run forward, plant your foot. You're going to push to the right, and friction's going to push you in the direct to the left. It is the friction force. It is the friction force that is causing the car to stay in the circle. The friction points towards the center because if the car had its choice, I mean, Newton's first law, an object in motion remains in motion. An object at rest remains at rest. So kind of at this point, the car wants to kind of keep going, right before that, the car wants to go that way. Friction keeps it from going there. If you had no friction, you ain't going in a circle. You had a patch of ice, your car, say it hit ice here, it's going to keep going straight. You need friction to stay in a circle. If I take a step and I try to push to the left, if the floor is really slippery, my foot's just going to fly out from underneath me and I'm going to fall on my face. I ain't moving to the left unless there's friction. So, why did I mention this problem? What's the point of this? Remember our bread and butter, y'all. Our bread and butter. MA equals the sum of all the forces. MA equals the sum of all the forces. That's been our bread and butter that we've been doing with these. Well, let's just do something really subtle here. MAC, let's just replace A with AC. All the acceleration towards the center equals the sum of all the forces towards the center. Centripetal force is not one of the forces that you add together. Centripetal force is not one of the forces that you add together. Centripetal force is the sum of all the forces pointed into the center or away from the center. Centripetal force is the sum of all the forces pointed into the center or away from the center. It is this MA. It is the left side of the equation. That is the thing I have to wrap your brains around when you're doing these problems, and it is a tool. Centripetal force is a tool to calculate things going in a circle. All right, so there you go. Look, it's the things I said. F net equals MA when you're going in a circle. A equals AC. And then we can set that equal to the sum of all the forces that go away or towards the center. Centripetal force equals the sum of all the forces pointed away or towards the center. Okay? So there you go. It is not a physical force. It's a math trick that equals the net forces. And it's very, very useful. It's a very useful trick that lets us calculate things that otherwise would be a pain to calculate. So, there you go. That's the major concept, y'all. This right here, part here, this is the major concept that is going to be tricky to wrap your brains around, but once you do, you'll be good to go. Yeah.
Why is it VT squared over R?
Yes, that VT squared over R. So that's a throwback to last week. Last week, I taught you all that centripetal acceleration is VT squared over R, where VT is not velocity times time, it's tangential velocity. So this is a throwback to circular motion. I told you all, hey, we're going to cover circular motion so that we can do some forces. This is why. Yeah, it's a good question. Do remember that VT is not velocity times time. It is not velocity times time. Remember, subscripts are adjectives, not variables. So T stands for tangential. All right. Okay, and look, it's the same slide, but a little bit nicer maybe. So there you go. It's a force that makes the body follow a curved path. It is not a physical force. It is a math trick. Just the more times I say it, maybe the easier it will be to remember. I don't know. That's my hope. Centripetal force is one of those things that is notorious for tripping people up. People always like to add it. People have a challenging time using this. But it really just comes down to centripetal force equals the sum of all the forces pointed towards or away from the center. Both count, towards and away. And we're going to do some examples today utilizing that. And that'll be kind of it. Like, look at that. We just got 3 more slides, and that's kind of everything I need to teach you today. Then I'll quickly kind of run through the rest, and then we'll do our lab. run through the rest as in like I'll say some things. I'll say, hey, this isn't tested, but just, to have in the back of your mind somewhere. All right. At the top of a roller coaster loop, you know what? Let's reword this. At the top of a roller coaster loop, what forces add together to equal centripetal force? And I'm actually going to change all these. Ooh, I did bad. I'm going to delete this question. I know you didn't have a chance to answer. I'm going to change this because I don't like the way these are worded. Is it Fn plus Fg? Is it Fg minus Fn? Is it F?
Whoa.
Let's control F. Fn minus Fg. Or, I don't know if there's another option I can actually list. Is it just Fn? Or you know what, is it just Fg? There we go. I like that better. At the top of a roller coaster loop, what forces, and the key here, if you're towards the center, it's positive. If you're away from the center, it's negative. Draw a free body diagram. Draw a little box up here. Draw the forces acting on the thing. Draw the arrows. And then the key here is that centripetal force equals the sum of forces towards the center. Towards center, positive. Away from center, negative. We're going to ask this question.
I didn't the grades.
No, I'm sorry. No, I'm sorry. I'm going to trust that it's very useful. And yeah, you can edit my assignment. Yeah, so you can either make a page or you can edit my assignment and add it as a link to the lab assignment if you want. It's up to you. I would probably put it on the lab. So when they open the lab, if it's right there, they're more likely to actually click it. Whereas if they have to go somewhere else, they're probably not going to. So I would just put the link in the lab assignment itself. Yeah, which is, it's going to be a little annoying because I have to put in all of them. At least for this lab. Maybe in the future, I put it like in the files tab or something.
I think files would just be fine.
Yeah, that's fine as well. Gravity is down. Which way does normal force point? How do we determine the direction of this? Tracks. Perfect. And we have a cart on the track. So then if it's stopping it from moving up, it's going to point. It always points away from the surface. Normal force always points away from the surface. If they're both towards the center, all right, y'all got 10 more seconds. In 5, 4, 3, 2, 1. All right, y'all. Here's the key. We draw our forces on it. Okay, gravity's always there. So which way? Gravity is straightforward. Which way is that point? Down. So FG is pointed down. There is another force. What's the other force acting on it? Normal force. And this is where you got to be careful. Normal force does not, it's not based on the direction of gravity. Normal force has nothing to do with the direction of gravity, as crazy as that sounds. Normal force is always opposite the surface. Normal force is always opposite the surface. If I lean on a wall, it's the wall pushes away from that. If we're at the top of a roller coaster, the normal force points down. The normal force is helping keep this thing in a circle. It is preventing the roller coaster from flying upwards into the air. When it gets to the top, the surface pushes down on it to keep it going in that loop. So to that end, according to this, centripetal force equals the sum of forces towards the center. Towards the center is positive. This is how we define positive and negative when we talk about circles. Towards the center, when we talk about centripetal force, is positive. Away from the center, we define as negative. To that end, it is going to be the first option. They are both positive because they are both pointed towards the center. This is a fantastic problem that kind of exemplifies centripetal force. And then you can think about what it would look like at different parts of this. That's a good thought exercise to kind of test yourself here. Okay. So let's do a couple problems. I'm actually going to swap these around. I'm going to swap these around because this one looks like the thing we just did. So let's do that. And then we'll do the other one, and then we'll jump into the lab for today. So a child of mass 40 kilograms in a roller coaster travels in a loop of radius 7 meters at point A, which is at the top of the loop. The speed of the car is 10 meters per second. That's just shy. That's like 25 miles per hour. And at point B, the speed is 10.5 meters per second. Point B is over here. I know it's hard to see here. This angle is 30 degrees. What is the force of the car seat on the child at point A? What is the force of the car seat on the child at point B? And what minimum speed is required to keep the child in his seat at point A? So, we're going to look at point A. Shock and awe. Free body diagram. You've already drawn the free body diagram for this, so thankfully I can just put that here. It's FG down, and it's FN down. We just decided that in the last problem. It's the exact same situation. I'm going to write down, actually, you all just try it out. See if you can figure this out. Remember, when you're going in a circle, MAC equals, I'll even put that over here. So, I'm not going to put it there. MAC equals sum of the forces toward the center. Remember what you all just figured out last question. Last question, you found the centripetal force equaled Fn plus Fg. Use that. I'll write that because I'm so kind. You all just decided, you literally made this decision. What forces add together to equal the centripetal force? You told me that Fc equals Fn plus Fg. Use that to solve this problem. What are we solving for in this problem? What is the force of the car seat on the child? What variable is that? It is the normal force. This question, if it ever asks, what is the force of the surface on the thing? That is normal force. You have to translate that in your head. All right, try it out. And if you can do A, part B, you have to draw a new free body diagram, and there's going to be angles involved, and see if you can figure that out. Well, we'll at least draw a picture for it for you all. We might not solve it all today. We'll see. Yeah, so part A is fairly straightforward. They just added adding greater than Fn plus yeah. Oh, yes. Yeah. And A being the part B, they have to find the component. Gravity that points towards the center. And that's the only difference. Yeah. This question I just have to separate. How would you figure that 5 years? So you basically divide it by your the average person. Yeah. So you take that divide by squares. So it's like a quarter, which is like noticeable. Oh, I from that no idea. So my neighbor it's cool. So it's in right. And so actually Tesla train goes 0 to 60 in 2.6 seconds. Calculate the acceleration which sounds really silly, but like think of the acceleration. You know those launch coasters? When you floored it, it felt like they which is nuts because the things they don't have to say what's the force required to do that. Which is yeah, it's it was interesting. Wait, I mean, I think this would be. I don't think it has any consequences. The other cars. Yeah, which is not ideal. Yeah. So for part A, you set this up and you're in what's the equation? NAC. And then what's the equation? So you replace this with Z squared over R. So you replace this with G. For which part? The force of the car seat on the child is. Oh yeah. So if you want the acceleration at point A, yeah. You do need the V squared over R, and that's the real price right here. Yeah. And in this case, it's not the hardest. It's actually not hard. Nope. No seat. Which you're fine. Any rotation. Oh. Yes. Yep. Good. No. Oh. Let me give you all the answers. As always, it's good to actually know if you're doing it right. How do you know if you're doing it right if you get the answers? There's the answers. So the key here is what you solve for. See, what variable did we say corresponds to that? The force of the seat pushes on the person? What do we call it? Nope. So I'm looking. I see something. I look right up more. Yeah. Is it great? Yeah, but it's great. Yeah. And you can either reach it. I don't know how long this sabbatical lasts. Yes. Perfect. He is fantastic. He is very much interested in all that are also interested. He's really, really good at that. He is one of the, so I think He's a very rigorous person, but not in a bad way. Like, so if you're interested in really learning it, he's gonna push that. So like for example, he was really interested in getting involved in high schools and doing the science and so he's very interested in like pushing that, like people to learn a bunch of things. So that can be really beneficial. And he has a really big interest in investigation. Nice. Good. Good. And you're a freshman, right? Oh, okay. Junior year is pretty common when people start as well. Sure. It's up to you. Working with someone for a year is fine. If you recommended the other person, it's not a bad thing to leave a group. Kind of thing, especially if it's similar stuff and you're shifting to another person, and you can even clarify that with that individual. All right, to give you all stepping points, I didn't write down the givens. I kind of skipped around. Mass is 40 kg. The radius is 7 meters. The velocity at point A is 10 meters per second. The velocity at point B is 10.5 meters per second. Generally, I can tell how a problem is going to go for people based on even just steps 1 and 2. As silly as it sounds, being able to match numbers to variables is a very, very important skill that shows a very important part of this class. Like, if you can't identify what's given, you can't do anything. So I keep stressing that. Do these steps. Practice these steps. Practice these labeling. So like I call this VA, and then I called the other one VB. Just even notation stuff is really important to practice. So that when you look at your problem afterwards, can you actually understand any of the math you did? Look at any of your previous problems. If you look at your previous problems, you're like, I have no idea what I just wrote down here. Either that means you don't understand your notation, you wrote it really sloppily, or you just need to refresh that content. Whatever. All right, great. We are solving for that. And so the key here, I already kind of wrote it down. Centripetal force equals Fg plus Fn. So mv squared over r equals m times g plus Fn. Solve for Fn, and then you're done. You have m, you have g, you have Va, you have r. Solve for Fn, that is the problem. So this one is just math.
So when you have FC, good.
Not in this problem. Positive and negative is all frame of reference. In these problems, if you're going in a circle, towards the center. Yeah. And a key thing to remember here, this is a good point. Remember, in this problem, down is not negative. In this problem, down is not negative. When you're going in a circle, positive towards center, negative away from center. We define centripetal acceleration. It is impossible for centripetal force to be negative. It is impossible for centripetal force to be negative. V is squared. R is always positive. M is always positive. So we define towards the center as positive because that's the only sign that centripetal force can be. Fc is always positive. And so it turns out, if we draw this in our picture, Fn plus Fg gives us our net force. Our net force is Fc. Our net force is Fc. That's the punchline to this whole circular stuff. When we do circular stuff, our net force is Fc. That's how we set up these problems. All right, so I'll give you all a few more seconds on this, and then I want to give you all the Obviously, you can start part B. The key to part B is a new free body diagram. New free body diagram for part B, where you have to find the forces that point towards the center. Yeah. Gravity's always going to be you can't get rid of gravity. When the normal force doesn't exist, that means the seat is. Because think about when they're getting pushed into the seat, that means the seat's pushing back on them. The minimum is at which point their butt is like just starting to stop pushing on the surface. That is the definition of when they're going to start moving off. They're no longer pushing into the seat. The seat is no longer pushing. Yep. How y'all doing? The next part. Nice. So, for part B, which way does gravity always point? Gravity always points down. The normal force will still point towards the center. That's free. You're gonna have to find the component of gravity. That's the key to part B. Normal force still points towards the center, so move but the gravity you actually find. You do that. The third, so we're all, this is all for part A, right? This is all for part A. The way we set it up for part A, we'll have to kind of the givens and steps. We are still for the normal force part B. We have to draw a new free body diagram, and then we'll use that Yeah, what's it? The one that points the sum of forces. So our equation is sum of forces that point towards the center. So that's the other way to get it. The one that point towards the center equals All right. So for step 4, it's just plugging in numbers and you get the answer here. I'm going to jump to part B. So I'm going to copy and paste all this. If you didn't finish part A, excellent problem to keep working on. I'm going to copy. All right. Part B, you have to draw a picture. Free body diagram at part B. You know what? I can draw it on the picture itself. Why not? Makes my life a little easier. Go ahead and try this. If you haven't done so already, I'm going to give you all like 30 seconds. Try to draw the forces. I'll give you a hint. It is gravity and normal force. But the directions, that's the key. Draw the forces at point B. Give you all like 20 more seconds and then I'll reveal the magic. Gravity always points down. Gravity's easy. Always points towards the earth. And then normal force. Normal force points towards the center. There we go. Now, here is the key. This is the thing I keep stressing to y'all. In circular motion, we do this. The centripetal force equals the sum of forces towards / away from the center. Y'all tell me, does Fn point towards the center? Yay or nay? Yay! We don't have to do anything. Does Fg point towards the center? Does a part of Fg point? Does a component of Fg point towards the center? Yeah, can we draw a triangle? Yes, we can. We can draw a triangle for Fg where it's a little... Here, I'm actually going to draw it off to the side because it's a little hard to see here. We can get the part of FG that points towards the center. The other part we don't care about. We only care about the parts. If you're using this equation, FC equals forces towards the center, we only care about the parts that point away or towards the center. So, my challenge to you all, is it FG times cosine of theta, or is it FG times sine of theta? We have the angle of 30 degrees, and at the end of the day, this problem, so you're going to get the part that points towards it, so it'll be FC equals Fn, positive because it points towards it, plus the part of gravity that points towards the center. That is how you're going to do part B. It's always, when it comes to circles, this is how we use this. This is how we use this trick, this centripetal force stuff. So try this out. See if y'all can figure it out. In a few minutes, I'll give it to you. And then I'll quickly talk about part C, and then we'll kind of have a 5-minute break or something and do the lab. Okay. We'll actually won't be able to get to this problem. However, I will probably do this problem on Tuesday during our review day. So feel free to do it before then, but I'll probably do this problem about the car on a curve on Tuesday. Tuesday is just problem solving. Cool. Yep. Yeah. No, just put it as positive. Always put it as positive, and then that's where you put plus and minuses when you put it in equations. So your triangle here isn't the right one. Is it the triangle you're looking for? The reason being, this, so you need FG in the hypotenuse. Here you have it. So how do you make it a right triangle? Yeah. Yeah, so a really good question is FG here is the hypotenuse of this triangle because it's the total. We're finding the components of it. The total is always the hypotenuse. The total is always the hypotenuse. The total is always the hypotenuse. So in this picture, here's my FG. How do you make it a right triangle? And this kind of just takes some practice with these. It's I know that I need this part of it. I know I need that part of it, and then I just connect that line, and this is a right triangle. You know that your components can't be bigger. Yes. So, yeah, your components can never be bigger than FG. Fantastic point. Yeah. If you magically got a bigger FG, it's hard. Yeah. The part of FG points towards the center can't be bigger than FG itself. I'll do that. We'll move on. Oh, yeah. The answer for B is 290. Yep. You have the hypotenuse, you want the adjacent, you have the... How are you all feeling? Sure. Just make certain that's m times g. FG is m times g. Yep. Yep. You find the component of it that points towards the center. The track has to work harder to keep you on the circle, because before gravity was helping keep you on that circle, on the sides it doesn't help. Yep. If y'all haven't realized this, what I want to point out to y'all just as a checkpoint, I say if you haven't realized this, as a checkpoint, this angle here, this angle is 30 degrees. This angle is 30 degrees. How do you know that? Parallel line theorem. Parallel line theorem. Check it out. I got a line here. I got a line here. I have a line that intersects them. Yeah. Oh, yeah. Is that what it's called, actually? Yeah. Opposite interior. Yeah, I don't even remember the names of them. It's terrible. I gave you this angle, and if you look at your picture, that's the same as this angle. Remember, I warned you all, geometry, you will need to remember some of these, like, things. This one is a bread and butter one. This one's really, really useful. Parallel line. It's not parallel line. It's whatever. Opposite interior. Names. So to that end, FC equals Fn plus Fg times cosine. Because it's the adjacent. This may seem like a pain, but this is your future. Like, look, I'm going to warn you all, a lot of your engineering, mechanical engineering, aerospace, maybe not electrical, maybe not others. If you're in anything with physical objects, you got to get good with geometry. Civil engineers, bajillion %, you got to be good with angles. And being able to take an angle and use it to find another angle. Yeah. Totally works. Science 16. Both valid. There's the trig identity that cosine of an angle equals sine of an. So, it's the same. 8.3. Oh, that's the only one that's just on. Yeah. And if you get part B, move on to part C, where it says what's the minimum velocity they need to move. At part A, you have to realize something. To figure out that, what's the minimum velocity, you have to think about what does that mean for them physically at that point. I'll give you all some time, and in like 5 or so minutes, I'll give the punchline for part C. Yeah. It's, the minimum velocity. It's not all. Oh. 9.8. Oh, yeah. No, it's not always 9.8. Yeah. At point. Question. So the truth is basically what's the criteria for that? Not much. It's actually the same setup for part A. But there's a special. You're going to use the same setup. What's the key here? What's the key there? When you're just on the ball, It's cell velocity. So, but think about, yeah, you have what's the thing that you feel right now? Because the idea there, when the normal force is zero, that reason the normal force is you're pushing on the seat. You're no longer pushing it in the seat, you're just you're no longer pushing the seat down on the seat. Gravity still exists, which is good. You're going to start pushing gravity. Yeah, that's the trick. Any velocity, one velocity, using that same weight. Instead of 4 days, just set it and you go to 0. Oh, okay. Yeah, what's up? So here, FG is your hypotenuse. You're finding the FG is the total. You're finding the component of FG that points towards the center, which needs to be smaller than that. Yeah. So your triangle here. So it's not this triangle. It's actually a triangle like this. Yeah, because FG center being bigger would mean that somehow gravity toward the center is bigger than the value of gravity itself. Yeah. 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 But it's really important to understand why that is and how to draw these triangles and stuff like that. Okay. So this one is just a bunch of math at this point. The physics is up there. You just plug in the things. It is worthwhile to do this. Remember, if this wasn't making sense to you, do not start this problem at this step. At this step, it's math. It's not physics. When you are studying, when you are looking over this, when you are trying to learn, you should start this problem from scratch. And you'd be like, but that sounds like a lot, like that's so much work, and that's going to, yes, it is going to be a lot of work, and that's how you're going to learn. At the end of the day, it stinks. Learning is hard. If the analogy I always give is you're not going to gain muscle if it doesn't hurt when you're lifting weights. The same thing with learning. You're probably not learning much if it's not hurting your brain. It stinks, but that is a sign, that is an encouragement to you all. When your brain is hurting, that means your brain is really having to think, which means your brain is making new connections. If your brain is hurting, that means it is working. And if it's working, you are learning. As long as you are working in a productive way. All right. Part C. Part C, I'm not actually going to solve for you all. We're just going to talk through the logic. Part C says, what minimum speed is required to keep the child in his seat at point A? What minimum speed is required? And here's the way to think about this. The minimum speed, think of what you would feel like if you just barely made it to the top. If you just barely made it to the top, how is your butt going to feel? Like, this sounds stupid. How is it going to feel in the seat? If you just barely made it, are you going to feel that seat pushing on you that much? You're not going to feel the seat pushing on you at all. If you just barely make it through that loop, you're going to kind of feel weightless. If you're feeling weightless, what's the only force acting on you? Gravity. What happened to the normal force? Part C is doing the same setup as Part A with normal force of 0. Part C is the exact same setup as Part A, but the normal force is 0. And this is where you have to wrestle through and try to make sense of that. But what I kind of think about what you would experience if you just barely made it. You're no longer pushing into the seat, and therefore the seat is no longer pushing on you. Normal force is 0. All right. I'm going to give you all, we'll reconvene in like 5 minutes, so 9:17. So you can feel free to keep working on this. Take a break. We are going to start our lab right after the break. Our lab will be on inclined planes. You can open up the lab. Oh, if you want to preemptively, this is up to you. I got to delete all the groups again.
Yeah, I was wondering about that.
This is the only system I found that works really well. Goodbye, old groups. Hello, new groups.
Oh yeah, I need to go on the browser.
Yeah. Whoa. Yeah, that's just like you said. That's not fine. Well, that was what are you solving for? That's where it's important to keep track of. What are you solving for?
Okay.
I don't know. I really thought I
So that's, you always got to keep that in mind. In part B, what is it actually finding you, asking you to find? Which force? Yeah, what variable is that correspond to? The force of the car seat on the child at point B. Is that centripetal force? Is that normal force? Is that gravitational force? Is that some other thing? So it's not going to be. It's the force of the seat on the child. It's the force of the surface on the child. You are finding the normal force. Part A also asks you to find the normal force. Part B is also. The normal force for part B isn't the same as part A. Yep.
Yeah, it was probably like 600.
What's the equation for that? What did you use for part A? mv squared over r. Yep, at point B. Yep, always. That's why step 1 and step 2 are always paramount. What are you actually solving for is always critical. Yeah, because that'll help you make sure you're on the right track.
cheese curds and cake. So it's a mix of a cake
Always. Depends where you are.
Yeah, but we don't worry. And you know,
Exactly, that's what keeps you on the circle. There's no reason you should. Because think about what's going to happen at the top. When you immediately start doing that, start going down. You can only start going down if you start getting pushed down.
That almost pushes way down. It keeps that pressure on the seat.
Yep.
There's no push.
So there's a force on the seat for every force in the seat. So the question is, why does the seat push on you? Because you push on the seat. When you're at the top, you are pushing into the seat. And in return, the seat is pushing on you. The only reason normal things yeah, so that's where it all comes down. I mean, you could think of it as the normal force on the seat versus the normal force on the person. Depending on where you're looking at a problem, depends on the force you show. So, for example, if I push on this desk, the desk normal force is this way, the desk pushes me this way. My normal force on the desk is that way. Because like when we first started, yeah, they do, but they don't. So like in this problem, it's not required. Yeah, so that's an additional safety measure. Yeah, at least for this part. Now, if you're doing a corkscrew, then a corkscrew, you do need something holding it onto the track. Because when you do that turn, the thing is going to want to, and so there does have to be something holding it onto the track. Anytime you feel your body doing this, like lifting up in your seat, something has to hold the cart down. Yeah.
And then you get to the point at the top where it stops. And you're just hanging
Yep.
upside down.
Yep. And the fact that you stop moving means that gravity is the only thing and you'll fall straight down. So that's why for part T, you have to have some velocity to keep you in that circle. If you have zero velocity, you're not going to go in a circle. You're just going to fall. The velocity keeps you in a circle. Keeps you in a circle.
And so then B is just doing that same thing, but with the empty.
Oh, I'm going to modify the lab report on the fly.
I'm adding in the Google Sheets.
Oh, cool. Thanks. Okay, so I'm going to spare them.
Part C, you're trying to find a page velocity. So that's why you
All right. I have spared you all and deleted part of the lab. But, it's still going to result in... So, hopefully, we won't be like at a mad rush at the end. But let's go ahead and start talking about the lab. So, as always, join a group. I've reset the groups as I do every single week. This so far has been a good practice because, as you can tell, various people are absent on different weeks. And so this makes certain every group has at least 2 people. You cannot be in a group of 1. So before we even start this lab, we will scroll through this. If there's any groups of 1, it has your name on it, so we'll know. We'll find you. You have to work with other people, y'all. They're called groups. They're, by definition, a group is more than 1 person. You cannot call a group me, myself, and I. Doesn't count. You are 1 person. So, if you are an individual, find a group with 2 people or find another individual. Make a new friend. Feel free to mosey around the room. So, as always, join a group. And then you can open the lab report if you want. You can start looking at it. We are going to design the procedures together again today. And I've actually deleted the procedures from the document. So you actually won't know how to proceed until we all do that together. But you can start reading it and looking through it and start coming up with a plan now. I'll talk about it in a few seconds.
Can you get a fee?
Yeah. One for you, one for someone else, I assume.
I just want to if you guys if I mess up.
Okay. Dude, that's fine. All right. Probably don't need the stream anymore. Do you think I should keep the stream going?
I think it's fine, yeah.
There's no harm to it, right?
Yeah. Sometimes you end up like saying
It's Google's story, not mine.
It's true.
All right. Presumably the lab is. Yeah. Someone is using it?
Yeah. I think it's
Where did you put it?
I just
Yeah. Also, we will be using Tracker today. Again. So be prepared for that. You can preemptively load it on the computer or your... So I actually probably need to put the link to my guide. Do you mind finding the... Oh, actually, I'll just add it here. I know where it is.
Okay. Hello, can I see lab group 4? Wherever you are. Okay. Do you guys mind adding someone to the group?
So we're not 4, my bad.
Oh.
That's fine. We'll just find their names.
I don't want to say something out loud on the mic. I feel like
Ah, it's fine. They'll be all right. Who's lab group 4? No one.
Kristen and Francesca. There we go. Okay.
There we go. That's easier. Oh, that's too many then. All right, there's got to be an opening somewhere. Group 14. Where's Alec and Julian? Alec and Julian? Alec, Julian? Oh, wait, there's a group of 1. Who's this? That's got 2 people.
15.
Dave, where are you at? Group of 2?
Oh, they're out of
You got 3? Darn. You have 2. Yay, we found one. Thank you. All right. So, today, our lab is going to be, remember I told you all that coefficients of frictions are not theoretical. They are measured. So let's measure them today. All right, so how are we going to do that? That's a great question that you're going to answer. I'm going to give you an inclined plane. I'm going to give you an inclined plane and a block. That's it. That's all you get. I mean, you have your phones as well, as always. And my questions for you all is, how could you measure the coefficient of static friction? Think of an experimental design for that. And then I forgot to put a part B here. How could you measure a coefficient of kinetic friction? They are 2 different things, and you will need 2 different procedures. So brainstorm. Given a block, given your physics knowledge, given a ramp, how could you find these coefficients using all the physics you know and those resources? Think about it. I'll give you all like 5 or 10 minutes to brainstorm an idea. We'll then discuss it. Very likely the ideas you came up with will be the ideas that will follow. But this is a skill. Given things, how can you find things? It's basically, it's a physics problem. So I'm going to go around, give you all the moments, and then ask you. How to? You could always draw some free body diagrams. I've got my alarm.
Right.
Oh, he has not mentioned this to you all. If you all use the group feature and you all like send messages to each other, we do get those messages. There hasn't been anything bad, but just know that we do see them. It's good to have transparency. So if you all send messages through the web courses to your group members, that is perfectly fine. That's like great, awesome. It's a great way to communicate with your group members. Just know that we do see those. There's been nothing bad, so I'm not saying that because there was like weird stuff happening. But I just want to have full transparency, so you know who sees what, you know, who has access to your data. That's the thing nowadays, right? No, that's just a feeling. No, that's how I got it to work. When I bring it to work, it does some things. There were some typos in this document because when I exported from Word to Google Docs, it got a little confused. You are not doing sine of sine. You're not doing tangent of tangent. That's obviously silly. So, you know, delete all those extras. future generations benefit from your suffering? All right. What strap do you all have? How can we find? I don't care which one. Okay. Sure. Think about that one. Do a free body diagram. Remember, you're going to use Tracker Pro. It's actually you get a lot of information. All right, so for static friction, it sounds like I've talked to a couple groups. Who feels confident? It could be one of the groups I already talked to. What is the procedure we're going to do? And I will open up a document that has the procedures all listed. So don't worry, they will be in writing this time. But yeah, who's got a strat? How can we find static coefficient of friction? There's a couple groups I talked to that said, yeah, that's a great idea. But there's probably many more of you that also have the same idea. How do? Be confident. Yes, thank you. What is it?
Put the block on the ramp and raise the ramp until it starts moving.
There we go, y'all. So, static coefficient of friction is the threshold at which point, we're going to find that threshold at which point it wins, at which point gravity wins. So let's, boom, there's my picture. We're going to call this the critical angle. The critical angle is the angle at which point static friction starts to lose. So if we put a block here, remember you got FG down, you have FF this way, you have FN this way, and we break FG into its two components. We want to find the magic spot where FG and FF exactly equal each other. And if you tilt it just a little bit more, it starts to slide. And when you find that threshold, the math is kind of worked out here for you all. So somewhere. So at that magic threshold, it works through the math. I'm going to let you all look through that and kind of try to process through how to get that. But it is worked out here, that magic threshold. Okay, great. That's for static friction. Let's think about for kinetic friction. Kinetic friction, you have many options here actually. So you're going to use Tracker Pro. Tracker Pro gets us good data. Remember, we get nice data with Tracker Pro. So Tracker Pro is going to let us, kinetic friction, am I moving or not moving? I am moving. So it's the same exact picture, but now my force of friction is smaller than my force pulling it down. And so all we're going to do is if we set up the equation, MA equals FGX minus FF, and we rearrange MA equals FGX, so that's going to be MG. I always have to think through this. Cosine or sine? Y'all tell me. Which one is the one pulling it down the slope? Am I going to do cosine of the angle or sine of the angle? So I'm going to think through the logic. Take your guess in your head whether or not it's cosine or sine, and I'm going to have to think through the logic in my own brain, and then hopefully it's right. So remember, I think of as the angle gets smaller, the FGX gets smaller. As my angle gets smaller, FGX gets smaller, so therefore it is going to be sine. Because as the angle gets smaller, so does the x component of gravity. That's how I logic through it. Great. Minus mu. Remember, F is mu Fn. Fn is going to be equal to mg cosine of theta because the component of gravity that points this way. All right. Great. Let's look at our givens. We can find the angle. We can find the mass. Actually, do we care about the mass? You know the angle. You know G. Use Tracker Pro to find A. Use Tracker Pro to find A. If you find A, you can do math to find mu. All right, so to that end, what I'm now going to do for you all. So what I've done this time, whether or not it was a great strat, we'll find out. To make it so people didn't jump too far ahead, I can't see Jack Squad here. I'm going to open the link to the, oh my gosh, I know it's me. Oh, it's one of those. I'm going to add the link to the instructions here. Right now it's refusing to let me see the name of my folders. Go away. All right, Fall 24, Studio. You can see all my wonderful organization. Week 5, Lab 4 procedures. Share. Boom. So if you want the procedures, the exact procedures to follow, and you go to the Lab 4 document. Boom, there you go. The reason I have you all think through how to design this lab is because this is critical thinking skills. What do I have? A block and an inclined plane. What do I need to find? The coefficient of friction. How can I design an experiment to do that? Then do it. It is the 4-step problem-solving process applied to physical systems. So it's practicing the 4-step problem-solving process in a different context. And it's a very invaluable skill. It's one thing to be able to follow a recipe. It's another thing to be able to come up with the recipe yourself. So there you go, y'all. Do it to it. Fill in your name, all that jazz. I know this says participation and contribution. That's nonsense. I'm not going to grade. Oh, that's just a mess to include that kind of thing. So there you go. In this lab, you're going to set the incline. You're going to do it for metal. I am going to have you do it for metal blocks and wood blocks for the static angle because that's really simple and that takes no time. I'm only going to make you do Tracker Pro for it sliding down when it's a wood block. Okay? So you're going to do the wood block and the metal block for static. You are only going to do the wood block for kinetic. I'm going to get a bunch of metal blocks. They're very heavy. And my phone has notified me that I need to take attendance. Here's my keys. There's metal blocks in there. I'm going to warn you, it's very heavy. Go ahead. Y'all can grab ramps. They're over there. You can grab blocks. They're over here. Mass did cancel, so you didn't actually need to know mass. But if you want to know mass, there's scales over there. Yeah.
When you get to that where you look at equation out or normal force, because you have normal force where not normal force, visual force where you use
Yep. Oh wait. Okay. Yeah. So okay, it's good. Yeah. So. Oh, and if you need a note card, don't forget to grab one. Yeah. So there's a component of gravity down the hill, and that's mg sine theta. Then there's a component that goes into the hill and use that to find the normal force, which you then use to find the friction force. It all.
That makes sense. You find your normal force and then you download.
Yeah, exactly. Here's y'all's metal blocks. They're heavy. They're metal. I don't care which size you pick. Doesn't matter to me. There's small ones, big ones. These are mostly big ones, but it really doesn't matter. Yeah, well, the whole crate. You carry the crate. I assume they're. I don't know what they're. I assume iron.
Yeah.
Probably. Just a solid. Metal's a lot heavier than people realize because you're used to working with aluminum. Yeah, aluminum's light.
It's like nothing.
Yeah, all of aluminum.
Yeah. Not the block I was here last time.
Yeah, nice metal block.
I guess I'll look at it. And they have really nice color too.
So we'll see how this lap goes. I don't think it's too much. Set the angle measure things. Set the angle measure things. Oh, wow, this is good. And as always, if someone's working on the first part static, another person in the group can be doing the video for kinetic. Feel free to split up the work. That's up to you. Oh, y'all probably don't need meter sticks because they're on the thing and you don't actually. Yeah. You don't need that. And you don't need that. No, you need that.
Oh, you put it back in.
Yeah. You are welcome, Devin. Maybe you want a meter stick. I don't know. If you want to measure how high up your thing is, feel free. If y'all want a meter stick, yeah, they're fine. Your thing actually does have the angle on it. I have not told you how to find the angle on this thing, so there is many options, and I'm not going to tell you how to find it. There's many ways to find the angle of your slope. Many ways to do so. Kudos, you can find the most efficient way.
There's no way there's this many people absent today. There's no way that many people are absent.
Yeah, when you first put it on,
If anyone didn't get attendance, raise your hand.
you do have to do 3 trials because it does seem silly. You're going to make slight deviations every time you take the measurement. More trials means more accuracy. Yeah, so I dropped
Literally almost exactly the brand.
Oh, does someone write their name weird?
I just want to know how to say it.
Oh. Yeah.
Sounds like a brand.
I guess we're supposed to use code.
It makes sense.
Yeah.
Do you have a protractor?
Nope. Maybe. I actually have no idea. Do we have protractors?
I feel like a protractor would be less precise.
I feel like a meter stick would
I'll
solve
tell
all
you,
of
you
it.
have a protractor.
It's true.
Wait,
You
actually,
have a
let's just.
device that can do all sorts of
Oh,
cool
can we
stuff.
do it with our phone?
Yeah.
Your phone
Okay,
has
there you go.
gyroscopes in it, accelerometers in it.
Oh,
There you
right.
go.
Apple has the like measure app.
Your phone has magnetic
Yeah.
field sensors in it.
Really?
There's so many sensors in your phone, it's wild.
Do we know them? No, you can use it. Yeah.
Oh, yeah, look.
Yeah,
exactly.
There you go.
You like these?
I still want my meter stick. I like those are too big.
What?
Those are what my buds do at night.
Oh, whoa, are they torsion?
If you haven't realized this yet, your phone is extremely useful and can be used to find angle. Your phone has a bajillion sensors in it, accelerometers in all 3 dimensions. A gyroscope to measure rotation in all 3 dimensions. It has a magnetic field sensor in all 3 dimensions. It has light sensors. It has sound sensors. The amount of sensors in your phone is nuts.
I did that too.
Yeah, Google used to have an app called like Google loves to just drop one.
Disappeared one day off of Google Home.
Yeah.
I would be so pissed if I but they had all my pictures. Yeah.
A meter stick.
Right there.
Yeah, so when you this is a this is
If I would have a phone, that might have a little bit less.
It's not changing at all.
Doesn't matter what angle because using practice you can actually, by taking videos, you can find static ones. When it happens, it happens.
You're good. Make certain you got your attendance stuff done. I'm closing this. If it didn't work, Leo, that thing, yada yada. Leo, where'd your right there? Yeah. Now, how sticky is it? It's up to you. It'll take too long to do. It'll probably take you like 2 minutes to do the measurement.
Would you mind going back to the equations you haven't gotten them down yet?
They're in the document.
Oh,
Yeah. All this? That's in the document.
okay.
Yeah.
For question 4, I imagine you only want us to compare static friction since we're not doing kinetic friction for metal blocks. Question 4 asks us comparing the friction between wood and metal blocks.
I have it for the wood block, and then I have it this one, right?
Yeah.
For the wood block, compare the coefficients, or is it up here somewhere? And I just didn't
Number
do it.
4 question.
So there's two. This part?
Yeah, we're not comparing the kinetic friction between metal blocks. We're not doing metal blocks.
No. Yeah, I deleted that. Yes, correct. Okay, I thought you were saying were you comparing it, the wood and the metal. Yeah, correct.
The PDF for the tracker guide says I need access.
Thank you. That's easy to fix. Thanks. Denzel. All right, for the tracker part of the lab, you have a choice. You can either do an incline, you can either have it slide down the inclined plane and use the acceleration for that, or you can push it. You can just push it on a flat plane. So I actually misinformed the group. You can just push it on a flat plane and use a video of that as well. The guide here is outlining how to do it for a flat plane. So if you're going to follow this, it's flat. If you want to do an inclined plane, you're going to use my stuff I wrote here. Up to you. I really don't care. I like the inclined plane personally, but you do you.
You can drop it
Oh yeah, I don't even know what apps. There's so many apps for Angle. One of the coolest apps that I recommend. Do you have Android or Apple? So. Okay, that was the one. Yeah, that was the one. I think so. so many things your phone can measure. Sound, lights. I haven't used it for many things. One of the things that I've always thought about doing, but I haven't done, is if I brought my phone on me with a roller coaster, which I've done before many times, having the accelerometer running, actually running it while you're riding a roller coaster, and seeing.
I had it running while.
Okay. Yeah, there's so many things you can use it for. Do you mind dropping my joke bag in my backpack?
Yeah.
Mine is still from back to last week. I have nothing.
Well, if you want to add me, I can give you a reference. Can I drop this today?
I'll probably, I don't know, if I turn this weekend maybe, but I have to today.
Okay. We used to have a red version, so is this supposed to be the same as this? Looks like
Yeah.
Okay. And then, so we use the
It's just an engine. So if you have 5.
And he like does the equation variation.
I used to they're not yours, I'll say. Very
Is it like a puzzle?
Yeah, the reason for that is it's going to be there's also just like yeah, you don't
As long as you
Just grabbing.
No, well, the way we did it was like this was horizontal, and we slid it right there.
That's one of the ways to do it. Yep.
And then I guess we'll just track the motion now.
Yeah, just one. Yeah. Google Docs has that issue for some reason. I don't know why.
Oh, I'm sorry. So this is for sliding. That's for if
For all the other ones?
yeah, that's all just a typo. It should be-
I've never seen it.
Come on.
It says otherwise.